Okay, so the board contains a summary of what we talked about last time. Rather messy looking structure here, and but hopefully today we'll understand it in a simpler way. So we are considering a rather basic problem in condensed matter physics. You have a metal described, say, by free fermions, and then you have a scalar field, which is, if it's representing an order parameter, it's close to the point where S is 0, so it's going to become critical. And in the absence of the fermion, this would be, that's the usual Landau-Ginzburg-Wilson theory of some phase transition in a metal. Later today, I'll also talk about the gauge field case, but for now, let's just imagine it's a scalar field. And then the two are coupled together by the simplest possible coupling. Just the density of fermions couples linearly to the scalar field. And depending on the problem you're looking at, there could be various indices and various different coupling constants here that depends on symmetries of the problem. We're just going to look at a simplified case where we just allow these set of couplings to be random numbers and average over all of them. And I gave various reasons last time why we think that's actually good enough for at least the starting point of the physics. And you get a large n limit, which is very well defined, and then we can think about corrections to that, although those are, as you'll see, quite hard to compute. All right, so if you take this theory and take the large n limit, you get the following set of 4 equations. So these are just Dyson's equations with 2 self-energies, sigma and pi. And the heart of the problem here is these expressions for sigma and pi in terms of the original Green's function. And this is, you can just see them from these diagrams. The electrons, the fermion self-energy is G times D. The boson self-energy is G times G. And these are fully self-consistent. So, you could just be happy with working with these equations. Sometimes they call the Eliashberg equations, self-consistent one-loop equations of a coupled boson and a fermion, and not worry about the large n limit, which is in fact the point of view many people have taken. But if you want to do something systematically, then this average of random coupling seems to be the only way, as far as I know. Okay, so then we are faced with the task of solving these equations. And I went through some rather elaborate evaluation of integrals for fermions and bosons. And at the end, we obtained a solution, which I've summarized here in this little box. And the physics of it is in this picture. So if you imagine you take the boson at some momentum q, then that momentum q defines 2 points on the Fermi surface, which I call k0 and minus k0. And these are the 2 points where q is tangent to the Fermi surface. And so I set up a coordinate system for the electron coordinate, electron momentum. This is the boson momentum q. The electron momentum, of course, is much nicer to measure it from the Fermi surface. Its momentum is really large, but this is where the low energy electrons are. And so I set up a coordinate system where kx is normal to the Fermi surface at that point, and ky is parallel to the Fermi surface. So then from that general structure, you get this dispersion. It's linear in this direction, kx, and it's quadratic in the other direction because it's tangent to the Fermi surface. And this kappa is the curvature of the Fermi surface there. So you can see that if you put kappa equals 0, then you'll get a flat Fermi surface. And then, those kinds of Fermi surfaces are called nested Fermi surfaces. And then it does become kind of one-dimensional. You have nesting between the two, and you get various logarithmic divergences that are very characteristic of one-dimensional Fermi gas. But we are assuming that that's not the case. Generically, there is some curvature, and we do have to keep it. Okay, so in this coordinate system of q and k, we obtain the singular low energy behavior of pi and sigma essentially exactly. So pi has the standard Landau damping form. This is an imaginary frequency, though that this is negative mod omega over q. But when you continue to real frequencies, it becomes imaginary and just gives you some very strong damping of the phonon modes. And so this is the final result I got. So rather hardly towards the end, but it's in the notes all worked out. If you want to see the integrals in great detail, the important point is you get a purely frequency dependent self-energy, which is omega to the 2/3. So in that sense, there's some similarity to the SYK model because there's no momentum dependence here. It's just omega. And it's some singular function of omega to the 2/3, whereas in the SYK model, it's square root of omega. And it's very different from the kind of singularity you get in one dimension, where you'll get omega minus k log of omega minus k at this order, which then exponentiates to a power law. So there's no k dependence here. That's not entirely true. There is some k dependence in the value of b, which depends on the value of VF and kappa. And VF and kappa can certainly vary as you go around the Fermi surface. But that's some smooth known dependence. It's not anything singular. It just depends on the position on the Fermi surface. All right, so that's a summary. And I thought it'd be good to see it, done the pedestrian way, where you actually just solve a bunch of equations. And now at least I'll give you some understanding of these features, including this 2/3, from a more from a point of view that quantum field theorists would find more palatable. Okay, but any questions? Yeah.
May I? Yeah. Can you clarify again why thinking of it as an infinite collection of 1 + 1 dimensional field theories is incorrect? You said that this is wrong.
Well, simply if you put kappa equals 0, this is kappa here, then this would blow up and this would vanish. You would just get, you wouldn't get the right answer. In a 1 + 1 dimensional theory, you'll get over here, the self-energy would be omega minus k to some power. And that's not what you get. It's actually independent of k when you evaluate the integrals.
Yeah, but physically, what's wrong with thinking about it as a coupling
well,
of
physically is that if you take a 1D gas in this direction, you're assuming that all the singular scattering events are all along this direction, and the different rays don't couple to each other. But that's not true. In fact, the most important scattering event of this electron is tangent to the Fermi surface. That's the lowest energy excitation, tangent to the Fermi surface, which goes as ky squared. If you go in this direction, it's kx, which is much larger. I mean, it's linear in k here and quadratic in k in that direction. So, or in other words, this density fluctuations, you could also take density fluctuation along this direction. That's what a 1D electron gas would say. You've got a 1D electron gas, say along this direction. So all the density fluctuations are also in that direction. You take density along this direction. And that, all the energies will disperse linearly with k. However, if you take density along this direction, it can have a much smaller energy going as quadratically in k. So that dominates. And that's ultimately responsible for the structure of k independence, but that's actually only true in the large n limit. Once you go beyond the large n limit, there are corrections, but they're very subtle and haven't been fully computed. I'll say a little bit about that in a few minutes. Yeah, you had a question. Sure. So if you look in the notes, I put an m here instead of an n. Then you have to take the large n limit with lambda equals m over n fixed. And then these formulae will have some factors of lambda in them, which is in the notes actually. Okay. Sorry? It can be either way. Lambda is just some number of order 1, and you send both m and n to infinity. And the important point is that the number of bosons and fermions should go together to infinity in some way. They just have to be proportional to each other. All right. So let's actually, before I get some of these results in a more appealing way, hopefully, I will let's just quickly review what the consequences of this are, this sigma of omega. So I want to analytically continue to real frequencies. So let me, for simplicity, just look at g of omega and kx, put ky equals 0, because that's orthogonal to the Fermi surface anyway. It's always a function of kx plus ky squared. And so this becomes omega. That's the bare frequency over here, first term. Then you have ek minus, that's just minus vf kx. And then you have the self energy, which is plus IB. Okay, now you have to figure out how to analytically continue this. And just to remind you, in the complex omega plane, all the expressions that we are now writing down are along this vertical axis. That's why there's an I omega here. And so you have to take omega positive, say, over there. So the sign will disappear if you want the retarded Green's function. And you just analytically continue it down this way or this way to get the Green's function on the real axis. So if you do that, this thing will just become, so this gives you minus I, which is e to the minus I pi over 2 omega to the power 2/3. Okay. So it's some function has both real and imaginary parts. And now you can take the imaginary part and plot it. So if you plot as a function of omega, you plot minus mg. Then at kx equals 0, well, first of all, this term is never important at low frequencies. You can just forget about it. It's needed at high frequencies to make the theory well defined, where you have at very high frequencies, you have the free particles, but you can just ignore this at low frequencies. And then if you also ignore, if you take kx equals 0, or if you say you're sitting right on the Fermi surface, then this is the only thing left. And so you will get a minus omega to the 2/3 divergence. Symmetric, if you work it out. So this is at kx equals 0. Okay, so that's what happens here at k. So there's no pole. So in a Fermi liquid, there'd be a pole right on the Fermi surface at 0 temperature in a strongly interacting Fermi liquid too. There's a delta function at 0 frequency. There isn't. There's only this continuum. In the SYK model, you get 1 over square root of omega. Here it goes as omega to the 2/3 with some prefactor. Okay, so that's for kx equals 0. If you take kx positive, that means you're going outside the Fermi surface. And if you're going outside the Fermi surface, it's easier to add particles than remove particles because it's mostly empty to begin with. So here, so if you take kx positive, you'll get spectral weight, which has a broad peak above the Fermi surface. So let me just look at the actual pictures are in the notes. So there is some dispersion. And yeah, so you get some picture like this and the reflection at small omega. So you get spectral weight at both signs. And then this will have a peak here, something like this. So this is for kx greater than 0. And for kx less than 0, it will be reflected. Okay, you can see actual pictures in the notes. All right, so this is all very broad as a function of frequency. But there's still the position of kx equals 0 is extremely well defined. It's the point where you have actually a divergence at 0 frequency. At any finite kx, in fact, this thing goes to 0 at omega equals 0, because you see if kx is finite and omega is 0, then the imaginary part of G is 0. On the other hand, if kx is 0, then the imaginary part diverges. So there is still something singular happening at kx equals 0. And so the Fermi surface, this is the basic lesson here. Fermi surface is sharp in momentum space, but it's very diffuse. It's not very well defined, and nothing special happening. No delta function anyway. But well, I don't know, diffuse, or if that's the right word. There are no sharp quasiparticle in frequency. I mean, this whole structure is, is very sharp. There are a lot of singularities. There's a singularity here, there's a singularity there, but there's no delta functions anyway. And these singularities here and here, just like that happens in the SYK model, they will be, they'll be rounded out at finite temperature. Actually, the behavior at finite temperature is a bit more complicated here than in the SYK model, because you have a scalar field in 2 dimensions at finite temperature, and that has, a lot of thermal singularities. Scalar fields in 2 dimensions have all kinds of logs that, leading to things like the costless-Thouless transition and things like that. So there are subtleties at finite temperature where you mix in with some classical effects that make the finite temperature behavior much more complicated and hasn't fully been sorted out. But okay. All right, so there's your Fermi surface without quasiparticles. Actually, at 0 temperatures, there's no such problems. It's all the theories in great shape. Okay. So this is what you would measure in a photo emission experiment. Okay, so now let's try to get the same results in a more systematic way. Of course, if it's one of those things that once you have done the hard work to do the solution of the Eliashberg equations, then the route to this approach becomes clear. Although, okay, it took a while before it was all sorted out. And but if you just try to do it in the beginning, it will seem somewhat arbitrary. But it's really based upon the insights that have hopefully become clear from this analysis. All right, so what we're going to do is we're going to focus on just these 2 points on the Fermi surface. So let me put them here in a sort of nicer coordinate system. So we're going to focus on this point and the other point. Okay, so this has coordinates. Now we're going to go to real space. This will be X and Y. And this will also be X and Y in the same direction. And I'm going to introduce a continuum field psi, which I'll call psi plus here, and another field psi minus. So just for simplicity, I'm going to drop all these alpha, beta, gamma indices. They go along for the ride. All right, so this psi plus this is something called the patch theory. It's not just describing the quantum fluctuations along the direction normal to the Fermi surface. No, it's describing it in the whole patch. So, and the theory that will actually describe the full patch here. But now you might say, well, what about the next point here? It's part of this patch, so it's part of this theory. But I could also define a different patch over there. Wouldn't also have a similar, that would be a different theory for the same patch. There seems to be some kind of double counting. Well, the answer is that in this, there is this theory that I'll write down has a certain sliding symmetry, which ensures that all those different theories connect to each other in a consistent way. But ultimately, if you're interested in a given point, you should work with that point because each point is characterized by different VF and kappa. And the theory would work for every such point. All right, so if I just take the free fermion part, that's easy to write down because I know the dispersion. So this Lagrangian for the patch theory would be the following. So I'll take psi plus dagger. It's d by d tau. It's dispersing in the x direction this way. So that'll be minus I d by dx. Well, put a VF there. And then in this direction, it's minus kappa over 2 d by dy squared times, I'm running out of space, sorry, psi plus. And then I can do it for the psi minus point plus psi minus dagger of d by d tau. But now I'm going to have the opposite sign plus I VF d by dx, because it's dispersing in the opposite direction, it increases in this direction. So these two terms are, in fact, exactly what you do in a one-dimensional Fermi gas. So you have two chiral fermions, but they're not one-dimensional fermions, they also disperse in the other direction. So you have to include the next term. Okay. All right, so that's just the free Fermi part. I could have always done this without any trouble in any free Fermi system. But now I have to couple it to the boson. Oh, I hope I didn't go too low. Yes, I did. Okay, well, I'll write it out again. Or maybe let me write the whole thing out. It'd be good to stare at this theory. So this theory will be connected to this theory. Okay, so I have L patch equal to psi dagger plus. Let me drop VF and kappa. Okay, use units so that VF and kappa are 1 and 2. Okay. All right, but anyway, it's starting to look like a field theory. It has a rather strange behavior where it's dispersive linearly in one direction and quadratically in the other. And there's two fermions and the two antipodal patches. Okay, then for the phi field, I just keep these terms. But I'm going to maybe separate them. The important term will be 1/2 d by dy times phi squared. And the other terms, I'll just put them down here because as you'll see, they just don't matter. And then finally, I have these terms. So these phi couples to both patches with the same sign. And so there'll be minus g phi times psi dagger plus psi plus psi dagger minus psi minus. Okay, so that's taking the long wavelength limit of this theory, and now I can feel comfortable in calling this a continuum quantum field theory. This isn't really a continuum quantum field theory because you've got these very large momenta here of order the lattice spacing. You've got a cutoff. So in fact, it's really only formally defined on a lattice, and there's nothing long wavelength about it, even though I took a long wavelength approximation here. But now I have decided that the low energy physics in these two patches, and now this is a honest to God Lagrangian, or if I want to write the action, S is integral d2x d tau times this whole thing. Okay, simple enough. If this was a Dirac fermion, then this would be called the Gross-Neveu theory, and everything is known about it. But it's not a Dirac fermion. It has a rather different feature. What's different about and makes this very, much more complicated is that if you look at the dispersion, it vanishes on a line. The dispersion here is E of k is kx plus ky squared. So that vanishes on the line, kx equals minus ky squared. So it's got a line of zeros, whereas a Dirac fermion has a point zero. And that makes it much easier to deal with. So it's all about this line of zeros, which is, of course, what the Fermi surface is. So even though it's a continuum limit, it has a Fermi surface, which is defined on these patches. But this theory also then poses a few regularization issues, which haven't been fully sorted out, I think, which is that I can't just put a cutoff where I cut the Fermi surface at some point, because Fermi surfaces never end. That will lead to singularities that you might have to worry about. But okay, so if you really want to do it consistently, you may have to come back to this theory. But for now, let's just see at least the saddle point we can understand from this theory. All right, so given this theory, we now can do the usual RG analysis. So this is what you do faced with any RG theory, any quantum field theory. You do rescaling transformation and figure out what's irrelevant and what's relevant. And then you do some RG transformation after that. So let's do that here. So let me rescale. X goes to X over B. In the end, B will become E to the L. And then you'll get some RG equation of the coupling with respect to L. So if X scales as X over B, then you of course want to preserve this form. You want to preserve the line of zeros. And so this tells me that right away that Y should scale as Y over B squared, or B to the 1/2, sorry. Let me just, did I make a mistake? Maybe it's B to the 1/2, yeah. Yeah, sorry, B to the 1/2. Okay, so this means another way of saying this, if X has scaling dimension -1, then Y has scaling dimension -1/2. So now the key thing is what do you do with time? So time, let's just leave it arbitrary. It scales as B to the Z. Z is what's often called the dynamic critical exponent. Now your first guess would be looking at this, that time should scale as the same as X. So Z should be 1, and Y scales with some exponent 1/2, and then the whole kinetic energy is invariant. You're free to do that, but then you'll end up with the theory of the Fermi liquid, because that's kind of the fixed point of the Fermi liquid, where energy goes linearly with K along that direction. And we also saw right up there, the omega term, this d by d tau term over there, disappeared in the low energy limit. So it almost seems this term should disappear. In fact, it shouldn't really be there. So at this point, we don't know how to fix Z. So just leave it arbitrary. Okay, so now we have chosen the RG transformation of space and time. Let's now look at the transformation of the fields in the usual way. So for example, how would psi plus and psi minus transform? They transform the same way, of course. So if you look at this, and it's better to write this out with X and Y because the X and Y scale in different ways. Okay. So if I look at this object here, X cancels with this X. So psi has to scale with 1/2 the scaling dimension of Y and tau. And that gives you psi goes to the B to the 1/4, well, plus Z over 2. So if you plug this transformation and this transformation into this term, you'll see it goes back to itself. If 2 powers of psi, that'll give you B to the 1/2 plus Z. And then the d by dx cancels with the dx. And the y will give you a factor of -1/2. The time will give you a factor of minus Z. And so you're done. Okay. Now you do the same thing for this term. Then what do you find? So this term also we want to keep, because remember my Q was in the y direction, and that appeared in an important way in all the calculations. So this term we want to leave invariant. We want to do an RG where, so let me underline the terms you're leaving invariant. The other terms we'll have to worry about later. We're leaving this invariant, and this one, and this one. Okay. So how does phi transform? Well, again, you work it out in exactly the same way. And what you will find, it actually, coincidentally, it turns out to be exactly the same scaling dimension. B to the 1/2, 1/4, sorry, plus Z over 2. Okay. So all of those orange underlined terms are now invariant under this scaling transformation. So finally, we want to look at this. We want to leave this invariant because that's the one that gave us all the singular effects. Without this term, there's nothing happening. So how does G transform? Well, so now you just have to put these numbers in for psi and phi and put it in here. And what do you get? I shouldn't write so low. So I'll go back up. Let's do it over here. All right. So what I find then is G goes to, if you just work this out, keep track of all the powers, then G will go to B times 3 minus 2Z over 4. Okay. So that's really just the simplest tree-level scaling analysis. I don't find any fixed point, obviously, unless, is there a fixed point theory here? Well, G remains invariant if Z is 3/2. In a tree level. Well, it's not really tree level because G is nonlinear. But anyway, if Z equals 3/2. Okay, So maybe that's a good choice, z equals 3/2. Of course, that's exactly the 3/2 right here. Kx scales as omega to the 2/3, or omega scales as kx to the 3/2, which is exactly this. So you will get the omega to the 2/3 for free. In fact, we know you get it, so there it is. Without doing any fancy calculation, there's the 2/3, which is the 1/z power of omega. Okay, so that is in fact the correct answer. And then what happens to the rest of the terms? The del by dx phi squared, they all flow to 0. They don't matter, which is, in fact, we never had to consider them in our calculation. They just disappeared, and they very naturally disappear here. So it's worth emphasizing this point. So I'll go up there and make those changes. So this term is there. So this is our theory now. And then the other terms just scale away to 0 under the scaling transformation. So, this term you can forget about, this you can forget about, and forget about. Okay. So there's our theory. It's not a free theory. It's theory where you're fixed Yukawa coupling. So it's sort of like a nonlinear sigma model, where you're fixing the Yukawa coupling.
Do you have
value.
any time derivatives left?
Yeah, so good point. So in fact, this theory has no time derivative at all. So how does any omega dependence appear? Yeah, well, that's actually the same is true in the SYK model. You throw out the time derivative, which is irrelevant. How do you get omega derivatives? So you do have to keep the d by d tau around. But in the end, when it basically tells you which direction you should close the contours and so on, and at least make certain the time direction u be finite. But once you're done, you can forget about it. Yeah. So that's exactly what happens in the SYK model too. The time derivative, you can't just throw it out immediately. You just have to keep it as you're going through the analysis for a bit longer.
What's the language for this in the context of the renormalization group?
What's the language?
So I did not formulate the question properly.
Well, this is, so renormalization groups generally start from some free field theory, where you have some free field theory and you find some rescaling transformation, then you take the nonlinear couplings and see how they flow. You can do that here too, and then that's been done. You have to introduce epsilon expansions and what else, but in the end, they always lead to some trouble. Here, if you wish, we're doing the 1/n expansion, and we're trying to understand the RG structure of the 1/n expansion. So in the 1/n expansion, was done at fixed G. So you could do it at fixed G, and we got some scaling structure. Now the prefactors of this result, like this B depends on G, but that can be absorbed in the redefinition of VF. And when you actually look at various critical properties, the value of G drops out. G basically sets the scale, and it drops out of any, as you'll see in a few minutes, by the end of this lecture, if I time it right, when we look at the instability of when you look at the scaling dimensions of some composite operators. Yeah, okay. But if you have some other way of analyzing that field theory, please go ahead. We'd love to know its properties. And the only method I know that's systematic for analyzing that field theory with the orange terms is this 1/n expansion with random couplings. So that field theory, it seems to get all the essential aspects of the critical Fermi surface without quasiparticle. It's surprisingly simple, but it's also deceptively simple, meaning because of the presence of this line of zeros in the dispersion of the fermions. Yeah. G is effectively, since it's invariant, and so order 1, it's the only scale there. So it's sort of like flowing to infinite coupling. In that sense, it's sort of like a nonlinear sigma model with a fixed Yukawa coupler. Okay. All right, so that's the quantum field theory, which is nice to see, and it simplifies. You can redo all the calculations in this language, and you get the same answers. But what you get for free for much less work is this value of z immediately of 3/2. I mean, similarly, you can also get the 1/2 exponent of the SYK model also through a similar sort of analysis without doing too much work. Okay. All right. So the next topic I want to turn to is really go back to this field theory and apply it to some other problems and see what's different about them, or if anything. And in particular, problem of a Fermi surface coupled to a gauge field. This was for autoparameter, but now we want to look at an honest to God gauge field. So I take, for simplicity, I'll take a U1 gauge field, but it's easy to generalize to non-abelian gauge fields. In the end, the non-abelian nature doesn't seem to matter at all. It only changes the number of scalar fields you have to consider. All right, so now we have a Fermi surface coupled to U1 gauge field. I forgot to say a couple more things about this theory. So one thing about this theory, it has certain emergent symmetries that the original theory doesn't. And one of them is a kind of a sliding symmetry that I mentioned, where everything, the fermion and the boson Green's functions are only a function of kx plus ky squared. And one way you can understand it is kind of like a spatial version of the Galilean transformation. If you think of x as time and y as space, then those two terms in orange are exactly the type of terms you have in non-relativistic theories. So there's some spatial analog of that. In this case, there's a sliding symmetry of this parabola, which is an invariance of this theory. Okay. So effectively, the theory has a certain one-dimensional character, but it's not same as a Luttinger liquid. It's one-dimensional in this sliding coordinate, dx plus dy squared. Okay, another thing you can compute from this theory, which I won't describe, and this will be described in a paper to appear hopefully in the next few weeks, is compute the auto-time autocorrelation function. And it turns out this theory, at least in the large N limit, also has maximal chaos. It's the Lyapunov exponent is exactly 2 pi t, and that relies crucially on this sliding symmetry and the local structure of the self-energy. So the fact that the self-energy, the SYK model, I mean, it's just a function of frequency. That's all there is in the SYK model. Here, it's as kind of an emergent fact about the large N limit, where the self-energy is only a function of frequency, and that leads to is one of the reasons you get maximal chaos. Okay, Fermi surface coupled to U1 gauge field. So now my Lagrangian would be the same as there before, and I won't go into the indices here. Some on K, there's some subtleties in how you preserve the indices and maintain gauge invariance. So d by d tau minus a tau, let me make it capital A, the tau component of the gauge field, plus E, simply we can write E of K minus A, the spatial component of the gauge field, times CK. Let me not put in the spin indices. And then I have, more important terms are del cross A squared plus, the electric field term, so this is just Maxwell theory, d by dx a tau minus d by d tau. grad A tau minus A whole square. Okay, so that's Maxwell theory coupled minimally to the Fermi surface. All right. So now you can actually make a few immediate simplifications with just a basic knowledge. How about the time component of the gauge field? Well, the time component of the gauge field is what mediates the Coulomb interaction. I'm not assuming it's non-relativistic here, actually. The velocity of light could be of order the Fermi velocity, which would be the case for an emergent gauge field. But that longitudinal component is screened. That's the basic property of a Fermi surface. It's a compressible system, and it leads to screening. The screening means that equal time correlation function, the force between static charges decays exponentially because of screening, and the dynamical excitations are pushed up to the plasma frequency. So those are the two sides of screening. And so that's all very non-singular. So if you just forget about A tau, throw it out. The longitudinal component is not important, and will work in the gauge. So this way they decouple completely. And that was called, I guess it's Coulomb gauge, which is del dot A equals 0. And forget about A tau. Okay, so now we can just apply the tricks we applied to this theory. We're going to go to these points and figure out what's going on. So let's say we did take the patch theory over here. So here the fermion dispersion is linear. So let me just take this expression here. So this will become in terms of those patch points. Psi dagger plus d by d tau. So it's linear in that direction, minus kx minus ax times psi plus. So that's it. And there's there's also plus kappa over 2, in principle ky minus ay squared times psi plus. Okay, well, what we see here, first of all, is that there's a coupling very much like the Yukawa coupling here between a sub x and psi dagger and psi. Just no derivatives because it's dispersive linearly in this direction. Just a times psi dagger psi. So we might think that at least as far as ax is concerned, it's going to have the same singularities. Like if I looked at Landau damping, that same term would appear in the polarization for A. So this means that if I'm thinking of the ax fluctuations, their wave vector is in this direction, because that's the wave vector for phi fluctuations that had Landau damping from these 2 points. Okay. So now remember I have this Coulomb gauge. So if my q is in the y direction, so q is pointing in the y direction, and that's the wave vector of A. So this tells me that qy times ay, because q is only in the y direction, is 0. In other words, ay is 0. So the Coulomb gauge tells me, forget about ay. So I'll forget about it. Okay. And that's all. And then I have this. Well, this term, since I've only have ax component, well, sorry, before that, I should write down psi minus. So there'll be psi minus d by d tau. Now it comes with the opposite sign, plus kx minus ax plus kappa over 2 ky squared times psi minus. And then I have this term, curl A squared, and also the time derivative. So that becomes curl A squared is d by dy of ax squared plus ay is 0. And then I have the time derivative term of the d ax over d tau whole square. Okay, so there's my long wavelength limit in the Coulomb gauge of a gauge field coupled to a Fermi surface. All right, and amazingly, only one component of the gauge field matters, which is the x component, and it couples linearly to the fermion density. So now the temptation, and I think I should probably go up there. Well, sorry. Yeah, let me go up there and make a few small changes. So what theory do I get? Okay, just to make my life even similar to the scalar field, I'm just now going to define AX is equal to phi. That's just a definition. All right, so then, I'm sorry you can't see it. You get these terms, you get these terms. You got this too. These would be relevant as before. The only difference is this sign is a minus sign. Because now the gauge field, I'm sorry, that's hidden. Let me show that to you. All right. Yeah, so if you look at this here, so it's always a function of k minus a. So here on the right-hand side, the dispersion is kx minus a with a minus sign out front. Here it is plus because the chiral Fermi move in the opposite direction. So ax comes with a minus sign here, and it comes a minus times minus with a plus sign here. Okay, so there's an opposite side coupling to the two. And in fact, that G is just the electric charge or whatever, which I didn't write down earlier. And I guess to be consistent, there should be a plus here. But that plus is not important. What's important is the relative sign between the two. Okay, so there's another way you can understand this relative sign. I hope I get this right. So if you had the positive sign, then this phi fields mediates an attractive interaction between the density of the fermion at the two edges, which is like two currents. Whereas this will mediate a repulsive interaction. And this is simply the statement that if you have, from Ampere's law, if you have two currents flowing in opposite direction, they repel each other. Is that correct? That's what this minus sign gets right for you. Okay. All right, so it's exactly the same theory, and for everything we worked on, this minus sign makes no difference, which is because everything would depend on g squared, and everything will be exactly the same, all the results that are presented so far. And so you'll get the same critical Fermi surface. If you put in non-abelian gauge fields, then there are higher order terms which preserve the non-abelian gauge symmetry. Those are all irrelevant by power counting. If you do the scaling analysis I did earlier, the a cubed terms just don't matter. Just like even here, the 5 to the 4th term, I just ignored it. They don't matter on that scaling analysis, where you put z equals 3/2. So the z equals 3/2, that makes all those other terms less important. You get, if you had an SU2 gauge field, there'll be a bunch of SU2 indices that you may have to worry about here. But other than that, and at the level that we've discussed things, it won't make any difference to the properties. Okay, so in some sense, the gauge field is no longer a gauge field, really. It just becomes a scalar field, and that scalar field is overdamped by the Landau damping. The propagator of phi, which is d of omega and q, it's 1 over q sub y squared minus I omega over q sub y. So as Qy goes to 0, this is extremely strong damping. In fact, you can also see the z equals 3/2 here. This tells you that omega scales as Qy cubed, but remember Qy scales as Qx to the 1/2, so that's Qx to the 1/2, 3/2, which is again the z equals 3/2 exponent. So there's the same exponent in both the boson and the fermion, and that's why they're so tightly coupled with this coupling G of order 1. So it's an overdamped gauge, and the gauge invariance really is not terribly important. All the all this subtle stuff that you have to worry about in relativistic gauge theories seems to disappear once you have a Fermi surface and you have the usual screening of the longitudinal gauge force and this much stronger effect in the transverse gauge force, which basically leads to overdamps the photon or gluon and also leads to loss of quasiparticles on the Fermi surface. Now, if you work this in 3 dimensions, the effects are weaker. In 3 dimensions, you don't have this strong scaling property. You get only logarithmic singularities instead of the 3/2. Yeah, so the situation, even though it's weakly coupled, it's not as well behaved in the sense of scaling. Yeah, okay. All right, any questions?
Sorry for being such a pest. I'm kind of keep asking you the same question. How should we think of such field theories? They are not considered as a free Lagrangian that we just flow using the interaction G. That's not what this is not what the picture is, or is it?
No, I mean, I think this is a strongly coupled field theory because G is order 1. Yeah, and
good. So so that addresses one. But then, how literally should we take it? So, is the claim that if I just take this theory, drop the irrelevant couplings, and just compute, we get everything correctly, or are there other counter terms that I need to add? What should I make of it?
Yeah, so in the large n limit, you will get all the properties I showed you, get it correctly. Then you have to look at 1/n corrections. And in the 1/n corrections, you get a new effect, which I also meant to mention. You get a small anomalous dimension for psi plus. So there is like a counter term, if you wish, of this gradient term. It's very small. Hasn't been computed in the 1/n expansion yet because it's really hard. It's been computed by Max Mitlitsky and in some other uncontrolled manner of evaluation of certain three-loop graphs. I mean, I'm pretty sure it's correct, but it would be better to do it in a more systematic way. So there is some renormalization and counter terms you do have to worry about associated with the dimension of psi. So there's an anomalous dimension for psi, which means that you have some cutoff dependence appearing there. So it's not a UV finite theory. But in the large n limit, it is a UV finite theory. It's perfectly well defined. So once you go beyond the large n limit, you have to worry about these additional logs that appear which give you an anomalous dimension of psi plus.
So
that needs to be understood better, but yeah.
What does that do to the marginality of the interaction? Does it make it marginally irrelevant, marginally relevant?
No, you're doing a calculation. You're not expanding the interaction. You're at the fixed point, and you're just computing a certain renormalization constant at the fixed point. So I don't think it destroys the fixed point. It's just a very small correction to the structure of the Green's function. So the self-energy is no longer just a function of frequency now. It also has some weak K dependence, but that appears at 3-loop order. I mean, there are also, in some sense, not quite the same, but issues of the SYK model also at order 1/n. That's where you get the Schwartzian theory, which leads to a breakdown of scaling. In that case, we know how to resum all of that in some very systematic way. Here, there is no breakdown of scaling, but there are anomalous exponents. So it's I think the belief is it's a conventional field theory, which has to be renormalized. The renormalization constants so far have been discovered for the anomalous dimension of psi. The anomalous dimension of phi is fixed. That doesn't change, and that's related to the fact that there is still there's a residual gauge invariance, related to this connection, and that's enough to fix the anomalous dimension of phi. So there's no normalization of the scale of phi. There is known to be normalization of the scale of psi. Then the anomalous exponent, and this relative scale of x and y is also fixed by the sliding symmetry. Then there's an exponent z. Is there a correction to the exponent z? No one's ever found one. Is z exactly 3/2, even at higher order than 1/n? We don't know. So, this systematic 1/n expansion only appeared last year. And I think there's a lot of scope for using it to answer some of these questions. These are, many ways, kind of open questions. They're also very difficult, to go beyond the large N limit. It's not a problem I would give any of my students, but maybe someone else would take up the challenge doing systematic computation of z and eta at higher orders than 1/n. It's very much, you have to do the analog of what's done for the SYK model. You have the saddle point equation of G and omega and K, and then you have these bilocal Green's function. You have to solve an integral equation to even determine the propagator. And once you got the propagator, you're going to compute additional loop diagrams. The path is well defined, but extremely rocky. Someone should do it, but no one's done it yet. Even for the SYK model, people have succeeded in doing it only for this one Schwarzschild mode. Beyond, there are all kinds of corrections there that are not understood. And that's a lot simpler than this. All right, so in the last few minutes, I want to address pairing. If you're studying high TC, the question you always get is, what is the value of TC, right? That's the $64 million question. So similarly, you can ask here, so then my answer is, well, I can't tell you unless I understand the strange metal, because it's coming from the strange metal. So now we have a theory of the strange metal, at least a possible theory. What does it predict for TC? That's really the key question we want to answer. Does this thing go superconducting? And if it does, at what temperature? Okay. That's still not well understood even in the large N limit because of these complications with the thermal fluctuations I mentioned. But at least at 0 temperature, actually, you can make a lot of progress and answer somewhat related questions. And this is, again, a topic of great interest. A lot of people are thinking about it. It's not, one of the difficulties is that this is a field theory that with a sign problem. You can't just put it on a computer and solve it. Unlike the Gross-Neveu model or something like that, where there is no sign problem. Okay, so let's talk about pairing. All right. So let me, now this is the place where this sign will be absolutely crucial. So let me replace it by a minus and call it, well, I don't know, eta. So eta is plus minus 1, depending on whether I'm looking at a scalar field or a U1 gauge field. And it turns out that eta equals plus 1 is the case where you have attractive interaction on opposite sides of the Fermi surface. Eta equals minus 1 is where you have a repulsive interaction. Now, for the U1 gauge field, the interaction is always repulsive because of Ampere's law. But for an SU2 gauge field, it can become attractive because you have this additional flavor degree of freedom. You can make the colors of the two fermions opposite to each other and make it attractive. So an SU2 gauge field is very, or SU3 or anything, you can choose the colors to make it attractive and get instabilities, from the quark-gluon plasma to the colored superconductor. That's exactly the type of calculation you do in 3 dimensions. Although in 3D, the patch theory is not well defined. because orthogonal to any Q, you have not 2 points, but a whole line. So it doesn't really help very much to work in the patch limit. But in 2D, it simplifies a lot because you can just work with the patches. All right, so just to remind you, I have a psi minus fermion here and a psi plus fermion here. And the pairing operator, call it O pairing, is psi dagger plus times psi dagger minus. So if you were in Nest metaphysicists, you'll say, oh, that's my pairing operator. So I got to sum the Cooper ladder and figure out what the Cooper ladder does. If you're conformal field theorists, you would say, well, that's a composite operator. Let's figure out its scaling dimension. Those are essentially the same statements. So we're going to solve for the pairing vertex operator. So you'll hit the operator here, and you call this the pairing vertex. So this is the operator. You have a psi plus here and a psi minus here. So you're creating a pair of fermions at opposite ends. All right. So that's going to be, well, you're looking at the 3-point correlation function, if you wish, between the O operator here and a psi plus here and a psi minus over there. As you often do, you just truncate the external legs. You just look at this vertex function. So then the leading term is just the bare term, of course, which is just 1, psi plus and psi minus. And then there's this term here, which gives you the sum of all ladder diagrams of the Cooper ladder. You have the same vertex, and then you have here the boson. So they're going to exchange a boson right here, which is the propagator phi, which is exactly this thing here. Okay. Now, when you do BCS theory, you could recast what we did BCS theory in the beginning of the course in this language. And there, essentially, this is some attractive interaction, which is, you just ignore the frequency dependence if you wish. And it's just the vertex is just a constant, and you just to figure out when it diverges, and that tells you when you have onset of superconductivity. So this is just summing, basically you're summing the ladder diagram of 2 particles interacting with each other over and over and over again, right? You put more and more of these interactions. Okay, but here the new subtlety is that this interaction is strongly frequency dependent. So you really have to think about this a little more complicated. You have to include the full frequency dependence of the pairing vertex. And that's in fact what Eliashberg theory was invented for, where the electron-phonon interaction, you keep the full dispersion, and then you have a pairing vertex, which is frequency dependent, and then you solve this equation. Okay. So the key to solving this equation, first of all, is looking at this loop diagram. Okay, we've got some pairing vertex, so we'll call that vertex okay, let me put some frequency labels here. I mean, we're just doing Eliashberg theory, but in a language which is more of a conformal field theory language than the Eliashberg language. Where does it go? Okay. Yeah, well, I didn't draw a picture. Oh, there's my picture. Okay, so I'll call this this thing here. Oh gosh. Okay, call this omega. Call this minus omega frequency. So this is the vertex delta of I omega. That's what this object is measuring. This is just 1. I'm cutting off the legs, and this would be, now I have again omega going out here, and minus omega here, and 0 momentum. But now I have this loop where I have both momentum and frequency. This will be minus omega minus k. This will be omega k. And this will be minus omega. No, that's a type 1. Oh, omega minus omega, that's correct. Times k. Okay. And this object here is now delta of I omega. So you can view this picture here as an integral equation for delta of I omega. So delta, we want to determine this function delta of I omega. This is just 1. And this is some integral of delta of I omega, where you put in the propagators here that we know. We know the propagators of the non-Fermi liquid here, here, and this one. Just put them in here, and we get an integral equation which you have to solve for delta of I omega. Okay, so that's a hard task, but you can do a trick. So you start from a regime. So the thing you know that you're starting from some kind of scale invariant state. It's a critical state of some type. It's got these very strange exponents, where x is scaling as 1/2 the direction of y, which is scaling as 3/2 the directions of z. It's got this very anisotropic scaling in space-time, but it's still got a scale invariance in it. And so you would expect, this delta of I omega, the vertex, which is basically like a 3-point correlator between a pairing operator and 2 fermions with some external legs cut off, that this should be just some power law of frequency. If the critical state was stable. So if it's a power law of frequency, in fact, it's particularly diverging, this 1 will not be important. Okay, so this is a trick that was used by Klebanov et al. For the SYK model. Is the same trick I'm applying here. So we're going to assume, so this is kind of where we're going. It's a quick way to figure out, is the system unstable to superconductivity or not, of pairing. Is there a condensate that develops or not? So we assume the delta of I omega is equal to some, well, in the normalization doesn't matter because it's, well, as if, yeah, okay. 1 over, we'll take it omega to some power alpha. Okay, so this is diverging and this is just 1, and we hope that this also diverges. So you throw out the 1, you just ignore this 1. So then this equation becomes something like, delta of omega is equal to, if you throw out the 1, there'll be some kernel that we have to figure out, k of omega and omega times delta of I omega. So that's what and this k comes from evaluating this internal loop integral over little, over little omega and k. Yeah, the little omega is there, just evaluating the loop integral over k. We're also assuming that this thing, and that simplification does happen, that this delta is independent of k. It doesn't have to be, but it'll turn out, like many things in this model in the large N limit, the k dependence just disappears. And you don't have to assume it's a self-consistent assumption. If you assume this is independent of k, the kernel, yeah, no, it's fine. There's no assumption really. Okay, you do the integral over k, you'll get this object here. All right, so this you can view, it's like a matrix equation. It's an eigenvalue equation. This is a matrix, and this matrix has eigenvalue 1. So would any arbitrary matrix have eigenvalue 1? No. So what do you have to play with? Well, you have to play with alpha. So you find alpha to solve this equation. It won't generically be solvable. If you solve this equation, so let's call this equation star to solve star. So if you get a reasonable value of alpha, well, then you're kind of done. Then you have this operator, which has a well-defined scaling dimension, which you can figure out. And so that just tells you how pairing how pairing correlations decay with time. They will, decay. This is a critical state. Any operator will have power law decay, and the pairing operator will also have power law decay. So in fact, that means if you find a nice alpha, that means there's no instability. System is well defined. However, if you try to solve this equation, so if alpha is real and well defined, there's no superconductivity. However, you'll find in some regime, alpha is complex, has an imaginary part. Okay, so now at this point, you don't really know what's going on, but a very reasonable assumption is that this whole assumption of a critical state is wrong, and the state is unstable to superconductivity. So this will be the region where there is superconductivity. All right. Okay, so so this particular problem, there has been work by Chubukov and others, but they've actually solved this equation in the superconducting state. It becomes a real complicated mess. But this particular equation is still a linear equation. It's just the analog of the BCS equation, linearized gap equation that we had for the BCS to determine TC. You could do this at finite temperature and to try to determine TC when alpha becomes badly behaved. There are some issues there that having to do with the fact that, the scalar field fluctuations at finite temperature have to be controlled in some reasonable way. So that's still a subject under some study. Anyway, so this is the analysis you have to do. So the only thing left formally is to just look at this integral here, okay, and figure out what the sign of the coupling is. And now you can see with this eta, which has disappeared, I'm sorry, becomes really important because this thing here is this coupling here is psi plus, psi plus, it's a coupling of psi plus dagger psi plus with phi, and this is psi minus dagger psi minus with phi. And so if they have the same sign, you get, the whole thing is positive. If you get the opposite sign, it's negative. And so that affects the sign of K. And that totally changes the behavior of these equations. So the bottom line is when you work this out, and you do that integral, the integral turns out to be extremely well behaved. You can just do the integral over Kx. So this is the only thing that depends on Kx. And the Ky dependence, when you do the integral, cancels out. When we do the Ky integral, it's only over here. And you get some expression for Kf omega and capital omega. Maybe I'll just write down the equation. So the net equation is the following. Again, the integrals are all worked out in the notes. So this is the case we considered. So I'll just give you the results. This was in this paper with Avishkar Patel, how you go and Ilya Aristoteles, just in the early part of this year. And many people have looked at this through other methods over the years. Okay, so what you get, this equation here explicitly turns out to be the following. It's delta of I omega is some constant I've got K over 3 d omega of delta of I omega over mod omega to the 2/3 that we had before, and then you get mod omega minus omega to the 1/3. And this, let me call it curly K or something. Curly K is equal to the following thing. It's M1 K2 to the 2/3 minus M2 K1 to the 2/3 over M1 K2 to the 2/3 plus M2 K1 to the 2/3. So what are all these couplings here? So K is that coupling K there, coefficient of grad A squared. And so we have M1 scalar fields, M1 scalar fields. Now I hope I get it right. If M2 is 0, that's positive. Okay, scalar field with an attractive interaction. And K1 is the coupling analogous to those, and M2 scalar fields with a repulsive interaction. Okay. So there's some ratio of the gradient term that survives that you have to keep track of. But very important thing is that G disappears. So you'll determine the scaling dimension of some composite operator, the value of the coupling goes out. So it is a scale invariant theory. There's just a dimensionless coupling constant here, which will tell you when you go superconducting or not. So the short answer is that we just have one scalar. If you have only purely attractive interactions, you will go superconducting. If you have purely repulsive interactions, you won't go superconducting, it's stable. And in between, there's a nice crossover. There's a critical value of this. And that critical value turns out to be something like 0.16. So K, this curly K equals 1 is purely attractive interactions when M2 is 0. And curly K equals -1 is purely repulsive. Purely repulsive interaction. So in fact, if you had just a very small, if you have just a weak attraction, then you don't go superconducting. But if you have only purely attractive interactions, you will. Otherwise, repulsive interaction, you don't. Anyway, so so those are nice results because it tells you that, for example, the spin-on Fermi surface is stable, and also the HLR state is stable because that has a U1 gauge field. But the nematic autoparameter, which is the scalar field with attractive interaction, is unstable to superconductivity, and so on. Okay, I think I will stop right there. Okay, so as I said, there's a lot more to be done here. This is still very much in progress, especially on the issue of what happens at finite temperature. It's a bit of a mess. All the beautiful scaling properties kind of break down at finite temperature here. But at 0 temperature in the large N limit, I think things are pretty well understood. Okay, all right, thanks a lot.
Let's thank Subir for all the nice talks and the lectures and also coming to Bangalore for this last part. So we're very happy and hopefully we're looking forward to your book.
Yeah, well, thank you for all the great questions, and it really helped me work through the book in many different ways. So yeah, hopefully the fruit will be evident when you see it. Yeah. All right, yeah, thank you very much.
I'd like to mirror these comments from Princeton. And we thank Subir for the wonderful lectures and for coming to Princeton for the beginning of this fantastic course. I, for one, just followed it very enthusiastically. I apologize if I asked too many questions. It's a sign that I'm really, really interested in this stuff. And
yeah.
the presentation was clear and stimulating. Fantastic. Thank you.
Sure.
And we're looking forward to your return to Princeton.
Yes, okay. Looking forward to seeing you, right. And this field theory I wrote down, which you had so many questions of today, yeah. If you have some ideas on how to solve it, that'd be great. But there's been a lot of work done on it and things related to it, and there's still a few open questions left.
Thank you, Professor.
And hopefully I convince you it's totally central to the most important problem. What is the value of TC? Okay, thank you.